Go on. So last time what we saw, we gave ourselves a proper summation pi from M to S with fiber X. So pi was a proper summation with fiber X. We gave ourselves a horizontal vector bundle such that Tm is equal to THM plus Ts plus Tx, where Tx is a relative tangent bundle, is a tangent bundle to the fiber. And so what we saw is that two things. First of all, that given this, we can identify the theorem space, the space of smooth forms, as a space of smooth form on S with values, with coefficients in the relative theorem complex. So this is an infinite dimensional vector bundle. And also that dm, the theorem operator can be viewed as a superconnection on the relative theorem complex. And we even gave a formula for this that I will just not explain anymore. So we wrote it as a connection, the sum of a connection, natural connection on omega of x plus a theorem operator. This is a fiberwise theorem operator acting again on omega x on the relative theorem complex. And then there is a third term which is the contraction by th, where by definition th, okay, so this is a section of lambda 2 of t star s, maybe I should say pi star of lambda 2 tensed with tx, and it's given by th of u and v, where u and v are in ts, is equal to ptx, this is a projector, minus ptx of vh, where u, h, and vh are the horizontal lifts, are the lifts of uv in thm. So, as we see, it's a non-trivial superconnection in the sense that it's a sum of a connection operator, and then there is this third term, which is a strange term, and which is there. Now, I will make some comments here on the question of self-adjointness. Okay, so I won't have time to develop much in this course, but I will just want to make some comments on this. So, first of all, let V be a real vector space of dimension n. Okay, so by definition, if alpha is in lambda p of v star, and if beta is in lambda of v star, I define gamma of alpha and beta to be minus 1 p plus 1 over 2 alpha wedge beta max. Well, max means that I just take it in lambda n of v star. So in other words, to get a non-zero term, I need that beta to be in lambda n minus p. Okay, so this is not, I mean, obviously the intersection product, alpha wedge beta, is not a symmetric form. There is a sign, but you can check easily that you have gamma of beta and alpha, which is given by minus 1 n plus 1 over 2 gamma of alpha and beta. This is an exercise. And so if by definition, we're now going to take alpha and beta to be in lambda of v star in the exterior algebra, complexified, and we define eta of alpha and beta bar. Okay, maybe I should say eta of alpha and beta to be I to the power n plus 1 over 2 gamma of alpha and beta bar. And so this lies in lambda n of V star complexified. So it's very easy to see, I mean, that's something proposition that eta is a Hermitian form with values in this space. So what this means is that eta of beta and alpha is equal to eta of alpha and beta bar. So, in other words, it's not a scalar product. I mean, it's not a Hermitian product. It's something else. And actually, this Hermitian form has signature infinite. Okay, so that's radically different from the usual L2 Hermitian products. And what one can check is the following thing that's very easy. So now that we have Hermitian form, you can always define the adjoint of an operator with respect to a Hermitian form. And so what I'm saying, I won't prove this, but it's not too hard, that if alpha, that's just an example of this, lies in V star complexified, then the adjoint, okay, alpha wedge star, so this is the adjoint with respect to the bilinear form eta, is just given by minus alpha bar wedge. Okay, so now what are we going to do with this? So let's say definition, if alpha and beta are compactly supported forms, okay, I just wrote with C to indicate that there is compact support, I'm going to define eta of alpha and beta to be the integral over M of eta of alpha and beta bar. Okay, M oriented, I assume here, M to be oriented. Okay, so in other words, by doing this, eta is a Hermitian form. I mean, remember that Hermitian form is just something which has a symmetry property that I mentioned before. When you exchange alpha and beta, you just get the conjugate of what you got before. And so it's very easy to see that proposition, if I take the theorem operator on the manifold M, and if I take its adjoint, with respect to this Hermitian product, then the operator dm becomes self-adjoint. So dm star is equal to dm. So this is radically different from what happens in usual, let's say, Hodge theory. When you construct Hodge theory, you construct an L2 Hermitian product, positive on smooth forms, and then you get an adjoint. D increases the degree, and the adjoint decreases the degree. Here, D is self-adjoint. So dm star is equal to dm. And so, in particular, if you form the sort of Hodge Laplacian for this new theory, what you get, the anti-commutator of dm and dm star, so maybe it's plus, that's the Hodge Laplacian, and this is 0. Okay, so for this exotic sort of Hodge theory, in which the Hermitian product is replaced by this Hermitian form, what you get as a Laplacian is 0. So more generally, if you have, let's say, E Hermitian vector bundle with unitary connection, nabla E as a unitary connection, you can exactly define on the space of smooth sections of, let's say, on the theorem complex of M with values in E, okay, so these are smooth forms tensored by E, you can define exactly an analog of the Hermitian form eta, and then what you find is that the adjoint of the connection is equal to itself. Okay, the connection, in other words, with respect to this exotic new pairing between forms, the adjoint of the connection is equal to itself, and so that actually, if you now form the Laplacian, the corresponding Laplacian, nabla E star, the plus here, this is just, okay, maybe I just put here a half here. Maybe what you get is the curvature. Okay, so what you get is the curvature of the connection. So this is just to say that in some sense the classical Chern-Weil theory is just in some sense a very degenerate sort of Hodge theory, is a degenerate version of Hodge theory in which the corresponding Laplacians are just now nilpotent operators, in which the Laplacian is a nilpotent operator. So in classical Hodge theory, let's say you have Laplacians which are elliptic operators. In Chern-Weil theory, we have nilpotent operators, and there will be exactly what I will develop in the last part of the course. This will be the hypoelliptic theory that will sit exactly in between the classical elliptic theory, Chern-Weil theory, which is now a Hodge theory, and in between there is a whole gray line, which is these hypoelliptic theories. Okay, so this is just a comment, but it will be useful to understand a bit of what I'm going to talk afterwards, which is the so-called refined version of the family's index theorem. So I assume now that X is compact, that, as we know, X compact, and we assume that Tx is spin as a vector bundle. So we already saw what means to be a spin manifold, and now there is a notion of spin structure for a vector bundle. That's easy. So we introduce GTX to be a metric on Tx. Okay, I should say here that X, also Tx, is spin unoriented and even dimensional. So also EGE, nabla E, as usual, Hermitian vector bundle with connection. And so we introduce the vector bundle STX cross E. And we saw last time that there is then the corresponding family of Dirac operators. So the Dirac operator, let me say, definition, that's the Dirac operator along the fiber XS. So instead of having one operator, we have a family of them. And so I explained that the family's index theorem is just consists in computing the Chern character of the index bundle. So we define the index bundle. So literally speaking, I define it as the kernel of dx plus minus the kernel of dx minus. And to simplify things, I assume that this have locally constant dimension. Okay, this is not really a serious restriction, locally constant dimension, so that indeed this is an element in the so-called K-theory of the base. So this should be viewed, I mean, you don't need for this course to know what is really K-theory, topological K-theory, but anyway. So you just take this as a formal difference, and the families index problem is to understand what is the Chern character of this index bundle. And so we know actually the answer, which is given by integral along the fiber of a roof of Tx, Ch of E. That's the Atiyah-Singer index families index theorem, and this identity is in H even of S with coefficients in Q. Now, as I explained last time, what we will do is refine this identity at the level of differential forms. Refine this at the level of differential forms. That is, we will try to replace cohomology classes by explicit differential forms and try to find to what extent is this equality true, still true in the proper sense at the level of differential forms. So, okay, so basically, I will say just a few elementary facts. So let me just give a few series of facts which for the moment they seem to be unrelated, which is to say the first thing is as follows. This is a very simple statement that that THM and GTX determine a Euclidean connection, that is a metric preserving connection on TX, GTX. Okay, that there is in some sense these two data determine a connection on this vector bundle. And so this this connection has these basic two properties along the fiber X, along the fibers X, nabla Tx is the Levi-Civita connection. Okay, so what I mean is that if you just differentiate a section along the fiber, vertically, you just have the Levi-Civita connection of the fiber. Okay, this we know what it is. And also that if U lies in Ts, then nabla Tx U, let's say of UH of A, so I'm just trying to differentiate sections of Tx in the horizontal direction, right? So I know how to differentiate them vertically, I just want to differentiate them horizontally. So the formula is, this is a very elementary formula, this is UHA plus 1/2 of LUH, this is Lie derivative operator GTX applied to A. Okay, so this is the formula. So, in other words, you could just use this term, UHA. As I explained last time, this Lie bracket indeed is tensorial in U, so there is no problem there. But the difficulty is that this does not define an Euclidean connection. So you just compensate for that by adding half of the, in some sense, half of the derivative of the vertical metric when you just deform the fiber through horizontal direction. So in other words, you have this picture here, you try to move along from fiber to fiber, and obviously this moving from fiber to fiber horizontally is not an isometry. So you have to correct this lack of isometric properties by this formula. So that's a canonical connection. Fact number 2. Okay, so what we're going to say is the following thing. To understand what is a family, to see what is a family of fibers, what we do is the following thing. In some sense, we make the fibers very, very far apart. So if you have a fiber manifold and you make the fibers extremely far apart, okay, you imagine that it freezes to 0 temperature. So in effect, the fibers cannot communicate with each other anymore, and what you see is exactly this collection of fibers. Okay, so in some sense, we're going to see this family of fibers as being actually coming from a regular Riemannian manifold, but in which the metric, horizontal metric, has been made infinite. So this is called passing to the adiabatic limit. This is an idea which comes from physicists, okay? The idea of adiabatic limit. So let me explain what it is. So what you do is that you start from a metric GTM. So this is a metric on Tm. And let me call THM to be the orthogonal to the fiber Tx with respect to GTM. Okay, so any metric defines actually a horizontal bundle, which is just obtained this way by orthogonality. Now, let me take GTS to be a metric on the base, and definition, I define the metric GTM epsilon, for epsilon positive, to be GTM plus 1 over epsilon, the pullback of GTS. Okay, so if you have a metric on the base, it pulls back because, I mean, if you take two vectors, you project them down, take the scalar product with respect to TS, and take the sum here. Okay, so making epsilon tend to 0, if you see what is the effect of making epsilon tend to 0, the effect of this is that it makes the fibers further and further apart. In other words, if you have two vectors which which are not vertical, their scalar product, if you take the norm, it gets extremely large, okay, because of this. So that makes the distance of the fibers as epsilon tends to 0 extremely large. Okay, so of course, when epsilon is equal to 0, this does not make sense. Okay, so this does not make sense a priori. Okay, but indeed, there is a first elementary observation, is the following thing. So first elementary observation, it is that proposition. So if I call nabla Tm epsilon to be the Levi-Civita connection, okay, so any metric determines this Levi-Civita connection, which is a unique metric torsion-free connection on Tm, GTM epsilon. Then, as epsilon tends to 0, the connection converges. It converges, so although the metric explodes, at least on non-vertical vectors, the connection converges. So it converges to a connection which is nabla Tm0. Let me write it this way, with respect to the splitting Tx and Thm, or Tx and pi star of Ts. So I write it, the limit connection, I write it in terms of this splitting. Okay, so it will be a triangular connection. It will be a sort of triangular connection. So there will be 0 here. Here there will be something that I will not describe, which is non-zero. And here I will get the pullback of the connection nabla Ts, which is Levi-Civita on Ts GTS. Okay, so what this means is that although the metric blows up, there is no limit metric, the family of Levi-Civita connections converge. They really converge extremely nicely and very easily. Okay, so this is not a complicated result, but this already says that certain structures survive, although from the metric point of view, in some sense, there is no limit metric point of view. And the consequence of this is that as epsilon tends to 0, A roof, let me just take A roof of nabla Tm epsilon. This is a Chen-Weil differential form associated with the A roof genius, I mean, it factorizes actually. It converges to a roof of Tx, nabla Tx, times the pullback of a roof of Ts, nabla Ts. Okay, and this is just a consequence of this statement, because the curvature of this limit connection essentially is triangular, but there is this two curvatures of Tx and of Ts which appear, hence this. Okay, so in other words, under a diabatic limit, the sort of Levi-Civita connection almost splits. I mean, it's not that it splits, but it just splits in a triangular way. Okay, so this is extremely interesting because this object here is the one that we would like to see appear in the family's index formula. So let's see how to exploit this. So I'm now going to define, okay, so let me introduce E to be the C infinity of X with coefficients in STX cross E restricted to the fiber X. So this is again an infinite dimensional vector bundle on which so dx acts on E. And so E splits as E plus plus E minus. Okay, so this comes from the Z2 grading of STX into STX plus XTA minus. So what we have under this condition is a section. We have this dx which lies in the odd endomorphisms of E. So if you remember, in the superconnection formalism, the most natural object that we had was a connection. Here, the one which is given to us is the operator. Okay, so for the moment, we don't have connections. So we're going to construct a connection. So actually, it's not difficult to construct a connection. So if U is in Ts, so we define nabla U on the vector bundle E. We're going to construct a connection on this infinite dimensional vector bundle. So if S is a smooth section of this infinite dimensional vector bundle, so let me explain how to construct the covariant derivative. So we just do the following thing. We have STX cross E, UHS, and then there is a correcting term. Okay, there is a correcting term that I will write as 1/2 of the divergence of UH times S. So let me just say that the connection here comes from nabla STX, which itself comes from nabla TX. Again, the connection on Tx induces a connection on the spinors, and so STX has a connection, and E also has a connection. So in other words, we say that to differentiate a whole section, let's do the picture here. Let's do the picture. So we have, here is, let's say, a curve. We're going to differentiate the section along, let's say, a curve, and U is a speed. So what you do is that we lift horizontally all these curves, we lift by them UH. Okay, so here are the integral curves, horizontal integral. And so basically, what we do is that we just differentiate the section S along the horizontal lift. That's the first term. But we have to add a second term. This second term, I will not explain in detail what it is. It is related to the fact that this horizontal bundle does not preserve the volume. It does not preserve the volume along the fibers. And since, okay, so this actually, it has a Hermitian structure just coming from the L2 Hermitian product along the fibers, and there is this question of the volume form. So the volume form is not preserved by this horizontal deformation, so you have to correct for these. So it is extremely easy to verify that this object is indeed a unitary connection, is a unitary connection on EGE, on this infinite dimensional vector bundle, which preserves the Z2 gradient. So this is quite easy. So this is quite easy. So now we are then in a sort of highway, and we are in a highway in the sense that we're going to put definition. We're going to do what we did in finite dimensions. We define AT for T positive to be the superconnection nabla E plus square root of T times dx. Okay, so in other words, we construct, now we have a connection, we have the operator, and we construct this. Okay, so this in some sense is a sort of nice object, because if you compute AT square, so as we know, AT square is not a differential operator on the fiber. The curvature of the superconnection lies in, if you just do the compute, that lies in lambda of T star S tensored with end of E even. Okay, and so this is also elliptic along the fiber. It's exactly like before, because essentially when you square these, you have first of all the square of this one, which is elliptic along the fiber, and then the other ones, all the other terms are nilpotent, so they don't count. They are nilpotent because they involve exterior variables on the base. So then we can believe that to prove the family's index theorem, we're going to define this object, which is alpha t, which is phi. This phi is just the scaling by powers of 2 pi, supertrace of exponential minus AT squared. So we do exactly what we did in the case of the proof of the index theorem, and also we inspired ourselves now from Quillen's theory. Okay, Quillen's theory was developed for finite dimensions, and now we extend it to infinite dimensions. So we do exactly what we try to do in the context of finite dimensional vector bundles. And of course, if the base is a point, then this is just the so-called what we did to prove the index theorem. Okay, so let me just state a theorem which is a negative one. Okay, so, but then I will correct it into a positive one. So first of all, okay, so maybe I write this as CH of E and AT, okay. So CH of E and AT is a real closed even form whose cohomology class is constant, does not depend on T, and is given by the Chern character of the index bundle. Okay, so in other words, we have produced by the superconnection formalism differential forms which effectively represent the class that we want to represent. But however, phi is a 2i pi normalization, usually in Chern-Weil theory. Okay, so when you have Chern-Weil theory, you need to introduce powers of 2i pi to the, you need to introduce the curvature divided by 2i pi or something. So maybe it's better to make 2i pi equal to 1. Okay, if you make 2i pi equal to 1, that makes life easy in many respects. Okay, so that's the first thing. The second thing is, okay, that the limit of CST tends to infinity of CH of E and AT. This is given Okay, remember that I assume the index bundle to be a bundle. There is no jump in the dimensions. Okay, so this will be actually the Chern character form for the index of D equipped with a canonical connection that I will explain what this is, Cn nabla ind of D. So this nabla ind of D that's just obtained by you just okay, so once you have a connection on E, since ind of D is a sub-bundle of the vector bundle E, right? So in other words, what I'm saying is that the kernel of D plus and the kernel of its adjoint are just sub-vector spaces of each of the fibers E. So ultimately they form a sub-vector bundle. So actually, since you have this, you can define the connection nabla ind of D to be the projection, the orthogonal projection on ind of D of the connection nabla E. Okay, that's a standard thing in finite dimensions. If you have vector bundle, sub-vector bundle, you can project orthogonally a connection on a sub-vector bundle. And you get this way, what you get this way is that you get, this will be a unitary connection with respect to the induced metric G ind of D. Okay, so in other words, E is a Hilbert, has L2 scale Hermitian product, so ind of D inherits it. Okay, so the remarkable fact is that the limit as t tends to infinity exactly converges in some sense to the differential form we would like to have in the left-hand side of a T-Singer, but however, sorry? So ind of D is a finite dimensional subvector space of E script. Right? The kernel of D plus and the kernel of D minus, they are subvector spaces. So you can always orthogonally project on this vector subspace. Right? So you apply the connection and you project orthogonally. Okay, so you get a connection on this vector sub-bundle. Okay, so in effect, as t tends to infinity, this has a limit. So, okay, so in some sense, we now have a family of forms which are constant in cohomology, and as t tends to infinity, they converge to, in some sense, the Chern character form of the index bundle. But however, if we make t tend to 0, if we make, let me say, 3t tends to 0, then things go extremely bad in general. So CH of E and AT essentially diverges as t tends to 0. It has an asymptotic expansion but extremely divergent, and so, we do not get anything out of this theorem, because of course what we would like to have is the limit as t tends to 0 to be equal in some sense to the integral along the fiber of some characteristic form. This is what one would like to have. And I'm going to explain how to correct this. I'm going to explain how to correct this, and again using the idea of adiabatic limit, and also in some sense also connecting what I explained in the case of the theorem complex. So we're going to cure this. We're going to cure this, and the cure will consist in adding a third term that I will call C of th divided by 4 square root of t. Okay, so we will have to introduce this third term, and then I will explain later on what is a third term, but when the third term is introduced, then 1 is true, 2 is true, but 3 becomes as t tends to 0, this converges to the integral along the fiber of the A roof of Tx, nabla Tx, Ch of E nabla E. Okay, so these are obvious Chen-Weil representatives. So now we indeed, with this we're happy. We have proved the family's index theorem in an explicit way, which is no longer cohomology. We have in some sense an explicit family of forms which interpolate between the Chen character form of the index bundle and the sort of form here for t tends to 0. So this is t equals infinity, t equals 0. Of course, we don't claim the forms to be constant. Okay, the alpha t are not constant, but the cohomology class remains constant, and so this proves the equality in cohomology. Of course, once we know this, since the cohomology class remains constant, this tells us that the cohomology class of this is equal to the cohomology class of the other one. So we have proved the family's index theorem. So we're just going to try to see how does this idea of adiabatic limits applies. So basically what we will try to do is build a sort of commutative diagram, analytic commutative diagram, which will explain why the proof is true. So to make things simpler, so definition, okay, so by definition for epsilon positive, I define the following object. This is a metric GTM epsilon. I changed slightly the definition I gave before. This will be GTX plus 1 over epsilon, the pullback of GTS. Okay, so this is a metric on TX, and this is a metric on THM. Okay, so I take a metric which is exactly of this form. It is exactly of this form. So in other words, it splits orthogonally into these two pieces. So also I will assume S to be spin. But this is largely irrelevant. I mean, the base, I assume it to be spin. So in this case, it's very easy to see that actually the spinors of M, I mean, in principle, I explained to you the spinors depend on the metric. But in this case, because essentially the metric is so simple, the spinors on M do not depend on epsilon, and they are given by STX. Okay, so it's a little bit unfortunate that you have S and S with two different meanings, but maybe we can afford to handle this times the pullback of the spinors on the base. So I'm simply saying that this total spinors, the total spinors is just the tensor product of the spinors of the fiber times the spinors of the base. Okay, so let me now explain what is the structure, okay, of the corresponding theorem operator on M. Okay, so this is a proposition. Let me call dm epsilon to be the Dirac operator for the metric exactly associated with the metric GTM epsilon. Okay, so this is a total Dirac operator on the total manifold M. Okay, so for the moment I don't look at the families. I just look at the full Dirac operator on the total manifold. Then this splits as square root of epsilon. I'm going to say this as being C of alpha nabla on, okay, on E times U, sorry, F alpha, with the F alphas here are an orthogonal basis of TS. Then I have the vertical Dirac operator, and then I have a third term. And this third term is given by minus epsilon C. Okay, maybe I put here a C of TH divided by 4. divided by 4, where now th, okay, now th lies in the Clifford algebra of Ts times the Clifford algebra of Tx. Okay, so in other words, a priori, this th is a two-form on the base with values in vector fields. Two forms on the base with values in vector in the fiber. But again, a two-form on the base can also be identified with an element of the Clifford algebra of the base. So if you like, this C of th, ultimately, it's an element of length 3 in the Clifford algebra, total Clifford algebra of Tm. Okay, so this is the structure of the operator dm, and if I also introduce, I scale the metric gtx by t, I just get here square root of t dx and minus here square root of t. Okay, so this is extremely easy to prove. That the total Dirac operator, for the moment it's not the family, it's just a total Dirac operator. So you observe in some sense that exactly the same thing happens as for the Duram operator. When you computed the Duram operator, we got Duram operator is equal to horizontal Duram plus vertical Duram, and there is a third term. So now we make epsilon tend to 0. We make epsilon tend to 0. And I explained to you that the limit of the Clifford algebra of a vector space when the metric tends to infinity, okay, that's the metric as epsilon tend to 0, this metric tends to infinity. I told you the limit is the exterior algebra. Okay, which means that in effect we have to replace this by f alpha. Here this nothing changes, and here in effect the element in the Clifford algebra of Ts are replaced by elements of lambda of T star S, and this then, this limit as epsilon tends to 0 is just AT. So in other words, the proper limit of dm epsilon t as epsilon tends to 0 is exactly the object AT that I introduced before. Okay, so how can we use this? Let me try to explain how to use this. So let me introduce the operator exponential minus, okay, maybe I now introduce the operator exponential minus t dm epsilon square. And okay, so I just take this, the supertrace of this. In other words, I take it's the heat kernel of this operator, and I take its supertrace. And now I'm going to make t tend to 0 here. In other words, we're going to justify the use of this new superconnection using a sort of commutative diagram. So, by the local index theorem, which I proved last time, what you get is exactly a roof of Tm, Gtm epsilon, times Ch of G and Ge max. This is just using what we did last time. Doesn't use any of this, of what I explained here. Now making here epsilon tend to 0, we just used what I explained, which is to say that the characteristic forms converge to the product ATS, nabla TS, ATS TX, nabla TX, CH of E, nabla E. Now let's go in the other direction. Okay, so this, I will just state it without a proof, but the proof is not difficult, given what I said before. This, as epsilon tends to 0, converges to ATS, nabla TS, times the form CH of EAT. This is not difficult. Again, I mean, it's not difficult. Well, except that in some sense we're now doing index theory, local index theory on the base with coefficients in an infinite dimensional vector bundle. So this is a bit difficult, but not too much. And so the idea is that this diagram commutes. Okay, the diagram commutes, and this can be sort of also justified. So ultimately, in some sense, the whole difficulty in this proof of the families index theorem is to say that, in some sense, handling families of manifolds is just a way of handling one single manifold, but with a metric which is infinite on the base, and we can do this. I mean, in spite of the fact that it seems we cannot, we can do this by introducing the proper nilpotents in the form of different exterior algebra of the base. So we have a proof, actually, of the families index theorem. Okay. So now, very briefly, transgressions. Okay, so in usual Chen-Weil theory, you know that if you take the Chen-Weil forms associated to different connections, you can express the difference of the Chen-Weil forms in a sort of canonical way as the D of some explicit form, which is the so-called Chern-Simons form. You know a little bit about Chern-Simons theory. Okay, that plays a very important role also in physics. So we have exactly the same sort of things here. So let me just introduce by definition. Okay, so I call alpha t, I just rename it for simplicity, supertrace of exponential minus AT squared with this new AT, and beta t is equal to supertrace of dA over dt exponential minus AT squared. Okay, so proposition, so this proof of this is proved exactly by the same techniques as in Chen-Weil theory. We have the fact that d alpha over dt is equal to minus d beta t. Okay, so beta t here is an odd, real odd form on the base. So what this identity expresses is the fact that the cohomology class of alpha t does not depend on t, but it expresses it in an explicit way. Okay, so let me define this definition. Let me define eta tilde. This is an odd form as being the integral of 0 to plus infinity of beta t dt. Okay, so this is a well-defined form because you can prove very easily that as t tends to infinity, this beta t is O of 1 to the t to the power 3/2, and as t tends to 0, it's a O of 1. Actually, the proof of this is just a consequence of the previous theorem. I mean, if you work things properly, you find that this sort of convergence at 0 to infinity are consequences of this. So eta tilde is a smooth proposition. Eta tilde is a smooth, odd, real form. Okay, to make these things real, I should have to introduce the powers of 2i pi, but I don't want. I mean, this would complicate things unnecessarily. And we have d eta tilde is equal to alpha 0 minus alpha infinity. Okay, so I remind you that what are alpha 0 and alpha infinity? Alpha 0 is just alpha 0 is just the integral along the fiber of a roof of tx nabla tx. It's a differential form, local one, times ch of e nabla e. And this other one is exactly the Chern character form of the index bundle. And so what this identity says, it refines on the family's index theorem in saying that not only these two forms are cohomologous, this we know, but the difference is the d of an explicit differential form. Okay, so one could say that basically the whole information about the family's index theorem is contained in this form eta tilde. It contains the whole mystery because it says not only the family's index theorem is true, but it says why. And the reason why it's true is because of this identity. Okay, so let me show how to apply this to the theory of the determinant bundle. Okay, I would say that eta tilde is already an object which contains a lot of number theoretic information about the family of index D. So, determinant bundle. Theory of the determinant bundle. Okay, so what I'm going to say is the following thing. That, first of all, if you take the CH of the index of D equipped with the connection nabla index of D. Okay, so this is now a finite dimensional vector bundle, a formal vector bundle, it's a difference bundle. Okay, and I just look at it in degree 2. Let me just take the component of this in degree 2. So this, by construction, it is given by the C1 of the kernel of D plus equipped with the connection kernel of D plus with a projector connection minus the C1 of kernel of D minus equipped with the connection kernel of D minus. This is just a tautological, almost tautological statement. Okay, the Chern character form is just in degree 2, it is the C1 of this. So let me define definition. Okay, so if E is a vector space, we define det of E to be its a line, which is lambda max of E. If E is a real complex vector space, and if lambda is a line, complex line, lambda minus 1 is a dual line. Okay, so on the category of lines, there is an obvious tensor product. I mean, I will not say too much about this, so that this notation is justified. So in effect, let me define the determinant bundle. Definition, lambda will be equal to the determinant of the kernel of D plus tensored with the determinant of the kernel of D minus 1. Okay, so for the moment we have made the assumption that all these objects have locally constant dimensions, so that lambda is a C-infinity complex vector bundle, line bundle, say. On the base S. And it is equipped with a metric, okay, that I will call lambda. This is the induced metric from the metric on G kernel of D. So the kernel of D inherits the L2 Hermitian product, and so the determinant bundle inherits this metric. Okay, so let's try to see what means this formula in degree 2. Okay, so what means this formula in degree 2? In degree 2 it means that D of eta tilde 1 this will be equal to the pi star of A roof of Tx nabla Tx Ch of E nabla E in degree 2. So it is this one minus alpha infinity in degree 2. This will just be minus C1 of this bundle lambda equipped with the corresponding connection. Maybe I should have said that the line bundle, since there is a connection on the kernel of D, there is a corresponding connection. Okay, so this is the interpretation of the identity I proved just in degree 2. And so let me definition. I just introduce the following imaginary one form, which is minus 2I pi eta tilde 1. Okay, so by definition, I introduce a new connection nabla tilde lambda, which is equal to nabla lambda plus gamma. Okay, so in other words, I had this original connection which was coming from you just look at the kernel of D, it inherits the L2 metric, it inherits the projected connection, and so it determinant, inherits a corresponding metric and a corresponding connection. And what I'm doing is, I just correct this given connection by the form gamma. So this is still a unitary connection, because I just corrected the connection by an imaginary one form. And now I'm going to say theorem. The C1 of lambda equipped with this new connection nabla tilde of lambda is equal to the integral along the fiber of Tx nabla Tx Ch of E nabla E in degree 2. Okay, so now this is quite extraordinary, because on this determinant bundle we have put a connection whose curvature is exactly in some sense the local expression which appears in the right hand side of Riemann-Roch, or Atiyah-Singer for families. So we constructed an explicit connection which is exactly the right hand side of Riemann-Roch or Atiyah-Singer, and of course the merit of this is that this is a local expression. But of course the price to pay is that we have had to correct this global connection by a complicated object which in some sense sees the full spectrum of the operator d squared in the fiber and also its deformation. Okay, so why is this theorem useful? Well, the theorem is useful because it has much more content than catches the eye. Okay, so extension of the theorem. So first of all, one can extend the theory of determinant bundles. Of determinant bundles, even when the kernel of d plus minus jumps. That is, even though I formulated the theorem in the case where I assume the kernel of d plus and the kernel of d minus their dimensions do not jump, the determinant bundle itself doesn't see the jumps at all. So this is the first thing. And so let me tell us in this context. So in other words, there is a certain line bundle lambda. I will construct it very briefly. That's is now a complex line bundle with metric, with double bar and unitary connection nabla lambda. Maybe I put a tilde here, which has two properties. So theorem, so there is this line bundle. So first of all, for any s, lambda of s is canonically isomorphic to the determinant of the kernel of d plus dx plus s tensored with the determinant of the kernel of dx minus s minus 1. So for each s, we have this canonical isomorphism of fibers. And the second thing is there's a C1 of lambda equipped with this connection is given by pi star of a roof of Tx, nabla Tx, Ch of EGE, nabla E2. So, of course, this is, of course, the natural theorem because, as you see well, the right-hand side here does not see the jumps in the dimensions of the kernels, the co-kernels, and so on. So it's probably the best statement as possible that ultimately we can get rid completely of these jumps. So let me briefly explain the construction by Quillen again of the determinant in this context, of the determinant line bundle in this context. So I explained again briefly what Quillen had done. Okay, so the construction of the line bundle, I will follow here Quillen. And as you will see, it will be quite easy. So let's say I'm just looking at my watch, so I have to go until 3, right? Until 4, sorry. Okay, so let me take here A positive, and I define UA to be the open set in S. It's a set of S in S such that A does not belong to the spectrum of dx squared S. Okay, so we know that the spectrum of these fiber-wise Laplacians or squares of the Dirac operator is discrete. So since the spectrum of dx squared is discrete, we know that UA is an open cover of S. It's open because as I mentioned maybe in one of these night sessions, the spectrum varies smoothly with the parameter. So, sorry, I should say does not belong, sorry, to the spectrum here. Okay, does not belong to the spectrum. A does not belong to the spectrum. Okay, so we have here A, and here are the eigenvalues, but A is not there. So UA is an open cover of S. Okay, so it's open because the spectrum depends smoothly, and it's a cover because the spectrum is discrete. So let me define the following space E0A for S in UA. S, this is the direct sum of the eigenspaces of dx squared S for eigenvalues smaller than A. So in other words, at each S, I just look at the direct space of the eigenspaces of dx squared for lambda smaller than A. This is actually a finite dimensional Z2 graded vector bundle. So E0A is a finite dimensional Z2 graded smooth vector bundle on UA. So let me define on UA, lambda 0A is by definition the determinant of a plus 0A tensored with the determinant of a minus 0A minus 1. Okay, so now this is a smooth line bundle on UA. So, okay, and so now let's see how to glue all these vector bundles together. So let me look at A smaller than B, and let me look at, I'm working on UA intersected with UB, so I have the line bundles lambda 0A, lambda 0B, and let me identify these two lines. I will now glue these two lines together on UA intersected with UB. So let me explain how to do this. So of course we have EA0B is equal to E0A plus EAB. Okay, we simply say that because B larger than A, we split the eigenbundle for eigenvalues between 0 and B as a direct sum, orthogonal sum of 0A and AB. So by using fairly obvious conventions, we find that the determinant of A0B in the proper sense, right? So I take this determinant as being the product of that E plus times the dual of the determinant of that E minus. So this is equal to determinant of E0A paired tensored with determinant of EAB. Okay, and now what I need to do is to show why are these two gadgets identified. Well, this is because I claim that this object here has a canonical non-zero section has a canonical non-zero section. So let me just explain why there is this canonical non-zero section. Well, this is because actually when you look at E plus AB and E minus AB, there is the map dx plus. Actually, because dx plus commutes with ddx squared, it maps E plus AB into E minus AB, but it is also an isomorphism. It's an isomorphism. It's an isomorphism because this interval does not contain the zero eigenvalue. So that's a very easy statement to check that as soon as you exclude the zero eigenvalue, dx plus maps 1-to-1 A plus into A minus. So this is a 1-to-1 map. So if you look at the so-called section, so then because of this, there is a so-called section determinant of dx plus, which is a section actually of the line determinant of EAB minus 1. So in general, the determinant of linear map is a number when it is an endomorphism. But when it is a map from a vector space into another one, and these two vector spaces are not sort of canonically identified, then the determinant of d plus x is a section of this. And since d plus is invertible, this is a non-zero section. And so because it is a non-zero section, by duality, this line bundle here also has a non-zero section that I will call determinant of dx plus minus 1. And so indeed, these two determinant lines are now identified by the product, by the two non-zero sections. Okay, so by definition, what we define to be the line bundle lambda is just the gluing, is just exactly definition by definition lambda is just defined by lambda 0a on UA plus the gluing maps lambda 0a equivalent to lambda 0b that I defined before on UA inter UB. And of course, the last thing to check is that these identifications are compatible with are a co-cycle. That is, if you identify UA lambda A with lambda B and lambda B with lambda C, you get the identification of lambda A with lambda C. But this is because, in some sense, this section here is multiplicative. Okay, so in other words, if you just can split again, if you have A, B, and C, this section that you get from determinant of A, C is just a product of the section from A to B and B to C. So, again, you need to be sure that the identification that I gave are compatible with refinements, right? So that's the line bundle lambda. And now, remark, let me fix S in S. So we have the exact sequence, 0 kernel of d plus, dx plus, gives E0a, gives E0b, and here gives kernel or co-kernel of dx plus or co-kernel of dx minus gives 0. This is at each point S. And so from this exact sequence, it's extremely easy to find that lambda 0as is canonically isomorphic to the determinant of the kernel of ds. So again, this construction has reconciled the fact that we have now a smooth line bundle, but each fiber is canonically what it should be, and still it completely ignores the fact that this kernel can jump dimension. Okay, so from everything that I said before, we can prove the theorem I gave before, which is to say that there is indeed a connection and a metric. Okay, so theorem, there is a canonically defined metric and connection and unitary connection on the line bundle lambda, such that the C1 of lambda nabla lambda is equal to the integral along the fiber of a roof of Tx nabla x nabla Tx Ch of E nabla E2. Okay, now the complex case. Okay. So, in this context, the ultimate goal is actually to show that these constructions that we have done are compatible with the constructions of direct images in algebraic geometry. Okay, so let now pi xms to be a proper summation of complex manifolds. So let E be a holomorphic vector bundle on M. So let R pi star of E to be the direct image of the sheaf OM of E. In other words, of the sheaf of holomorphic sections of E. So if you like, I don't know if you know what direct images are, but maybe the simplest case is to assume that there is no cohomology except in degree 0 in the fibers. To assume that, so example is the case where just there is the higher cohomology of XS with coefficients in E restricted to XS is equal to 0 for E bigger than 0. So in this case, R pi star of E is just H0. So in this case, by a construction of, okay, so in the general case, what we know is that R pi star of E is a covariant sheaf. And by a construction of Knudsen and Mumford, there is a certain holomorphic line bundle, which I will call determinant of R pi star of E. So there is, even though it's the direct image is just a coherent sheaf, you can construct the determinant of this, which is lambda, is now a holomorphic line bundle on the base S. And now the question is to know whether all the smooth constructions I gave, using the theory of Dirac operators and all these constructions I gave, which rely very much on the smooth category, are they compatible? Are they compatible with these algebraic geometric constructions? So I will here just mention one theorem. So assume that aim is scalar and that GTX is a fiberwise scalar metric. On the relative tangent bundle Tx equals Tms. So now we're dealing with holomorphic tangent bundles. Then, given a metric GE, Hermitian metric on E, then there is a canonically defined there is a canonically defined metric which I will call double bar lambda, smooth metric. Metric lambda on lambda associated with this data. This is so-called the equivalent metric. So canonically defined smooth metric, double bar lambda on lambda, such that C1, now if you have a holomorphic vector bundle with a metric, a line bundle, this defines a Chern connection. Okay, so contrary what we had in the smooth category, where metrics and connections are sort of disconnected, in the holomorphic category, the metric determines a connection. So once you have a metric on a line bundle, it defines a connection called the Chern connection, and from this you can calculate the Chern, the C1 form. And so the C1 form is given by now integral along the fiber of Todd of Tx GTX, because now I use again the fact that the Chern-Weil forms are determined not by a connection but by the metric. The metric determines the connection and the connection defines the Chern-Weil forms. CH of E GE2. Or I should say 1, 1 maybe. Okay, so this is a piece of degree 2 but which turns out to be of degree 1, 1. Okay, so there is such a metric and it's canonically defined. That is, it's defined in particular using the Hodge fiberwise theory, the Hodge theory and the full spectrum of the fiberwise Laplacian. So besides the variation, the dependence of the equivalent metric lambda on GTX GE is explicitly known. Is known, it is local, that is, it just can be computed using local quantities, and in some sense this dependence actually generalizes the so-called Polyakov anomaly formulas, generalizes the so-called Polyakov anomaly formulas. Polyakov is the Russian physicist, which prove this actually for in the case of Riemann surfaces. So the whole theory of anomaly, of the so-called anomaly formulas, extends to arbitrary dimension, and so also the functorial behavior of this Quillen metric under immersions and is also known. Again, I mean, this is starting to get hard. The results are not easy. And so ultimately, the purpose of this is to say in the algebraic context, what you want to have is exactly a metric on a determinant line like this in order to be able to count the number of integral sections, of algebraic sections of bounded norm. Okay, so that starts using the the geometry of numbers, Ziegel's theorem in counting points of lattice points and so on. So you want to construct such a metric. I mean, the use of this is that ultimately you construct this sort of metric, and that connects with Arakelov theory, but this I won't do this. Arakelov theory and Gillet-Soulet theory. Theorem of Riemann-Roch-Grothendieck in this context. Okay, so the proof of this essentially consists in showing that there is a compatibility between the smooth constructions I did before and this construction in the holomorphic category. Okay, so you have to work to prove that these are compatible constructions. In other words, you build on the smooth theory, and then you sort of check that these smooth constructions in the complex case are compatible with algebraic geometry, which is not, I mean, that's something that you really have to take seriously and prove, but the result is true. So next time I will just briefly a little bit elaborate on this and then move to the so-called theory of the hypoelliptic Laplacian. So I think my time is over. Thank you very much.